Okay, in this video I want to talk about absolute convergence. First of all, define what it is and then tell and explain why we care. So absolute convergence means that if you have a series, so you have a series like this, and you know that this series converges then we would say that this series, without the absolute value, converges absolutely. That's what absolute convergence means. Now, it sounds funny that when we hear the word absolutely, we make it sound like this absolutely converges, like it's for sure. But really what it means is that that the series by itself, we can't show that it converges maybe, but we can show that if we put the absolute value around it, we can show that that converges. Then we would say that the original series converges absolutely. Now, the reason why we care about that is there's a theorem that says that if you can show absolute convergence, it implies just regular convergence. So in other words, if this series converges, then this series converges. So that's the theorem that says absolute convergence implies convergence. Now notice that this is handy on a series that is alternating, which means it's every other term it's negative, positive, negative, positive. So if you're adding up a sequence that has every other term negative, positive, for example, if you think about an arithmetic sequence, like if you have the sequence 5 times negative 1/2 to the n. Okay, so that series would be, for example, a sub 3, for example, would be 5 times, we're letting n run from 1 to infinity. Sorry, what am I doing? This term, a sub n running from 1 to infinity of a sub n, would look something like this. If I plug a 1 in there, that would be negative 5/2. If I plug a 2 in there, that would be positive 5/4. If I plug a 3 in there, that would be negative 5/8. If I plug a 4 in there, that would be positive 5/16, etc. So you can see that the sequence itself is alternating, which means the terms of the series are alternating. So in that case, most of the series that we've looked at so far have been positive all for the all the way through it. So this gives us something to deal with, an alternating series. If we can take the absolute value of it and show that it converges, then we can claim that it converges. So for example, let's say that I'm trying to prove that this guy, n running from 1 to infinity of 5 times negative 1/2 to the n, we're trying to show that converges. Now, of course, we already know it converges because it's a geometric geometric series, and we know the geometric series if the absolute value of the r is less than 1. But we're going to try this little test on it. So let's, for a moment, consider this guy. Well, we know that if we have the absolute value of every term, then really this is going to be the same as 5 to the 1/2. Because the negative in there, all it's going to do is change negative, positive, negative, positive. It's not going to change the values at all. So we can say that this is the same as that, And this we know is the geometric series. So I guess I'm still using the geometric series test, but just showing that geometric series test works on negative ratios, just like it does positive ratios. So because we know this converges, then we would say that this one converges absolutely. Now, the key thing to remember about this test is it only shows convergence. You can't use the absolute value, the absolute convergence to show. There's no such thing as absolute divergence. So in other words, if I'm looking at a sequence like this, and I find out that this sequence diverges, well, that doesn't tell me anything about this one. Just because this diverges does not mean that that one diverges. So it only helps me if I can take the absolute value of it and I get convergence. That'll say the original series converges. If I get divergence, then it doesn't tell me anything. Essentially, the test fails. Okay. So let's look at an example here. Here's n running from 1 to infinity of -1 n minus 1 over n squared. And again, I can't use, that's not a p-series because it's -1. Well, it's -1 positive 1, -1 positive 1, so it's not -1. It's not 1 over n to the p. We can't really use a comparison test because the comparison tests only work for positive numbers, positive series. So what I'm going to do is, let's consider for a moment, let's consider this. N running from 1 to infinity of -1 to the n minus 1 over n squared absolute value. Now again, just like we did earlier, that would mean that's the same thing as 1 to the n minus 1, which of course is just 1 over n squared, right? Because 1 to any power is still 1. So, and we know that this converges because it's a p-series with p equal to 2, which is greater than 1. So then because therefore, this series, n running from 1 to infinity of -1 to the n minus 1 all over n squared converges absolutely. There's an E in absolutely, is there? Maybe there is an E. Converges absolutely, which implies that it converges. Right? So this is, again, it's a handy test as long as you can get convergence. It doesn't help to get divergence.